Okay, we're looking at 712 practice. The front side are light waves. So we are looking at this equation mostly, C equals lambda nu. Most of the time you're just going to plug it in. I think a few of these questions ask you to interpret this spectrum. So if you're looking at, here, the meters, which is the wavelength, you're just matching up to what type of radiation you have. Sometimes, and I think maybe this is the most difficult part because it's just algebra otherwise, is like converting and just making sure you're paying attention to units. So real quick, King Henry died by drinking chocolate milk. This is 0. This is 3, 2, 1 exponents, -1, -2, -3. And then we'll also have nano, which is -9, so it's way down here. If we're converting, we need to always have it in meters when we're plugging it in for wavelength. If we're converting, say, for example, from milli to meters, we're going to go back 3 places to the left with your decimal or subtract 3 from whatever exponent they're giving us. Same thing if they give us nano, we're going to go back 9 places to the base unit. And then, of course, if I was going base to nano, for example, I'd go 9 places to the right. So we're just moving the decimal or the exponent, depending on how you're expressing it. All right, so let's look at numbers 2 and 3. Number 2, we're looking for frequency. Again, we're using this equation, C equals lambda nu. All right, C is the speed of light, which is 3e8 meters per second. Let's go ahead and isolate or rearrange this equation. We wanted to solve for this here, so C over nu equals lambda. All right, so 3e8 meters per second divided by 1.2 e15 1 over seconds or inverse seconds. That's going to cancel out when you divide. So you're going to be left with meters, which is a totally acceptable unit for wavelength. All right, so we'll put that in. 3 exponent 8 divided by 1.2 exponent 15. And that's 2.5. If you move over the decimal, I would express this in scientific 2.5 e -7 meters, which a lot of times they'll put it in nanometers. If you were to add 9 to -7, you get a +2, which would move it over 2 places, so 250 nanometers. They didn't ask for that, but sometimes it's an easier way to express it. Number 3, we're still using this equation, the wave equation, but we are solving for frequency this time, so it's this one. So you're still using 3e8 meters per second, but this time we're going to divide by the frequency divide by the wavelength to get the frequency. So they're giving it in meters, which is good, but you should always check that because, again, our units need to cancel out. So I would recommend maybe writing your units out. Okay, so we are solving C over lambda equals nu. So 3e8 meters per second divided by 1.54 e -10. And that was in meters. Okay, good. So this will cancel out. Okay, and then we're going to be left with seconds, but that's really over once. It's 1 over second, so this is really going to be inverse seconds, which is an acceptable unit for frequency. 3e8 divided by 1.54 -10. All right. Again, I'd put this in changer mode, make sure it's in scientific. That is actually 1.95 E21. And notice I'm reflecting as far as sig figs, like what they give me in the problem. That's, we'll assume, is measured. And this is in meters. I'm sorry, inverse seconds. Or hertz. So frequency, again, is inverse seconds or hertz. Wavelength often is meters, can be in nanometers, centimeters, millimeters, whatever, but when we plug it in, it always has to be in meters. All right, on the back, this is what I call the particle equations. This is when electrons can behave as particles. So I'm going to just do number 7, since there's not as many of these on here. I think you'll just use that equation for most of these, except for maybe 11, because they're talking about wavelength and frequency. Wavelength is not in this equation. If you look, there's no lambda here, but there is frequency. So just use whatever you need to solve it. All right, so we're solving for energy. Energy equals H times nu. H, again, is the Planck's constant, so we just plug it in. So I believe they put 6.63. Sometimes it's 6.626. Doesn't matter. It's not going to make much of a difference. All right, joules times seconds times what they gave us, 6.8 E15 1 over second, or inverse seconds. Seconds cancel out. We're going to be left with joules. So clear that. 6.63 exponent negative 34 times 6.8. What was that? E15. Exponent 15. Okay, so what is that? Okay, that's 4.5 E negative 18. Again, change your mode on your calculator. 4.5 E negative 18. Okay, and that's in joules. And I get this means nothing to you, but when we compare, like in lab, these different energies, we're looking for relationships. So these numbers just help us quantify that relationship. All right, the rest of them, let's see, you're looking for energy in number 8 and energy in number 9, frequency in number 10, and then again 11, you might need to use the wave equation, but you can, try those out and then check the answer key.